Welcome to Lecture 6, Transport Optimization. In today's lecture, we define what is transport optimization, understand why it is important, look at the various types, and discover how it can be achieved through the use of artificial intelligence. Transport optimization is the process of determining the most efficient means of moving products to the customer while maintaining a desired service level given a static supply chain network. The customer can be an internal component of the company or the traditional external customer. From the carrier's perspective, transport optimization helps them to stay competitive by providing better solutions to their customers. In view of the increasingly low margins and constantly volatile fuel prices, it also makes sense to keep their transport operational costs low. From a shipper's perspective, global sourcing and global markets need to be linked seamlessly by an efficient transportation network to meet their customers' demands. This is especially so in view of the global trend towards a focus in customer service excellence, where service has become a critical success factor. Last but not least, from the environment's perspective, as we have learned previously, there's an urgent need to minimize transportation's impact. Government regulations, penalties, and surcharges are used to motivate carriers to run operations more efficiently. Let's take a look at a case study where transport optimization has helped to create a win-win situation for all stakeholders involved. We know that products are made in a factory, the manufacturer, and sent to distribution centers, but they are then distributed to retail stores where customers can buy them. Products are shipped across the supply chain on wooden or plastic pallets. Have you ever wondered what happens to them at the end of the chain? Pallet pooling solution providers are responsible for cycling pallets through the supply chain. Firstly, they issue ready-to-use pallets to manufacturers and distribution centers. When retail stores receive their products, they unload the goods and return the pallets to the depot. At the depot, the pallets are inspected and ensure that quality standards are met before they are reissued. An example of such a pallet pooling solution provider is CHEP. CHEP is the largest backhaul shipper in North America. They manage trips in more than 45,000 unique lanes and more than 20,000 locations through the use of sophisticated transport optimization systems. If you remember, we discussed the carrier's dilemma of the empty backhaul in Lecture 4. When a truck makes a trip from A to B, an empty backhaul occurs when there is no load for the return portion of the trip. However, if the truck can be scheduled to collect empty pallets from B or somewhere nearby to drop off at the depot near to A, then the empty backhaul is eliminated. This business model helps carriers to minimize or eliminate empty backhaul and generate additional transportation revenue. It serves the primary objective of continual recycling of pallets through the supply chain, and it eliminates empty miles and carbon emissions to increase sustainability. Overall, this becomes a win-win-win situation for CHEP, the carrier, and the environment. When people talk about transport optimization, it can be at two levels, tactical or strategic. Tactical transport optimization applies to decision-making in day-to-day routine operations. Strategic transportation optimization applies to more long-term, high-level decisions to be made for the company. Tactical transportation optimization is a process that usually runs daily, a number of times a week, or weekly through the use of software that is specifically designed for that purpose. Some operational constraints could consist of cost budget, how much does the customer want to pay, desired service level, when does the customer want the products delivered, are there any security needs, etc. Allowable product mix is also a consideration. Example, pharmaceuticals cannot be delivered together with dangerous chemicals. Lastly, equipment availability. Bulky and heavy cargo, such as aircraft landing gear, may require special cranes during delivery. Tactical transportation optimization takes into consideration all the defined constraints to produce an executable optimal solution for the delivery of products to customer at the desired time for the agreed cost. Let's take a look at a simple case study. To catch 5 Pokemons in SP. One day, you are at SP McDonald's and decided to play the Pokemon game. You were excited to discover a Snorlax at T11 Square, Lapras at the library, Dragonite at Starbucks, Pikachu at the Sports Complex, and a Charmander at FC6. Logically, you would set about catching them one by one by starting from the nearest one at T11 Square till the furthest one at FC6. But what if you were to discover that each Pokemon had a different residual life, the library is closing in 10 minutes time, and in addition, you need to go to T11 for CCA after you finish this game. And lastly, you are really just quite lazy and want to minimize time spent walking around the school. Of course, there are many ways to go around catching the 5 Pokemons in SP, but perhaps not all the routings you try might enable you to catch all of them in time. If you were to run a transport optimization program, taking into consideration all the constraints listed, this might end up as your optimized route. So you might ask, what has catching Pokemons got to do with logistic operations? Turns out it is not so different after all. Let's take the case of a logistics company which has cargo to deliver all over Singapore. The company needs to figure out what is the best routing for the delivery truck. Some of the constraints the company faces could be, for example, minimize distance traveled, avoiding peak hour traffic, offloading the largest orders first, making customer windows happen, and really just the need to go back to the warehouse at the end of every day. So a possible routing could end up looking something perhaps like this: meeting all the constraints and then allowing the truck to go back to the warehouse at the end of the day. Strategic transportation optimization, on the other hand, looks at more macro level questions, such as what transport mode should I use, in what proportions, can my orders be consolidated? Executing such an optimization will quantify the above questions and allow the management to make informed, concise decisions to address the organization's needs. Strategic transportation optimization takes into consideration trade-offs and budgets. Sometimes a higher cost has to be incurred to obtain the speed required and the need to fulfill customer service expectations. This must be done within the boundaries of the company's budget and reflect the worth of that customer's business for the company. Let's look at this case study in which a Singaporean company needs to ship goods regionally from Singapore to 5 different countries in the region, including Malaysia, Laos, Vietnam, Philippines, and Indonesia. Depending on the country, there may be up to 4 different modes to choose from. It is up to the company to define their constraints such as order lead time, acceptable damage rates, and budgeted costs. So how does one achieve transport optimization? Most methods use various combinations of historical data and reliable forecasts and actual orders and real-time information to arrive at optimized operational decisions to improve efficiency and customer service. Traditional transport optimization software use batch planning algorithms to create an optimal set of routes for each day's deliveries. What does that mean? Let's say there are only 3 locations to plan for. Then the number of possible routes is only equals to 6. This is easily visualized and can be planned using eyeballing and simple calculations. However, if the number of locations increase slightly to 10, you will quickly realize that the number of possible routes increases to a very unmanageable 3.6 million. Transport optimization software actually considers each of these alternatives. To provide more optimized solutions, then it is possible with manual planning as long as all the constraints have been entered accurately into the system. Modern cutting-edge transport optimization software tends to be more dynamic in nature. A real-time interface allows the tracking of deliveries and locations of all vehicles deployed. Drivers may be rerouted on the go using mobile applications when new situations arise, such as changes in cargo volume or collection locations. It manages trade-offs between optimal and feasible routes depending on what are the company's business needs. In order for a dynamic system to function, it must have real-time information being fed into it. For example, specific arrival times of vehicles can be captured using geofencing, a kind of GPS technology that creates a virtual geographic boundary, enabling software to trigger a response when a mobile device enters and leaves. Changes to expected cargo volume are also very common and will trigger recomputation. In some cases, customers may also refuse to accept deliveries or cancel their deliveries or pickups. Other important information may include customers' requests for priority deliveries or pickups, traffic conditions, vehicle accessibility, because certain buildings are only accessible to vehicles of certain sizes, and last but not least, country-specific labor regulations about how many hours a day a driver can drive. At a strategic level, integration of global inbound-outbound transport flows requires consideration of integrated production and transportation planning for manufacturers. The transporter must be able to move goods produced to free up space so that the manufacturing can go on. Workload at the distribution centers. The warehouse must be able to handle the workload associated with new incoming goods and orders for outgoing goods. And inventory management at retail sites. There must be a right balance of goods so that there's enough to satisfy demand and yet not exceed the physical storage capacity of the store. Many enterprise resource planning or ERP and transport management systems, TMS, support a number of transport planning functions. These include basic route planning, or could be advanced planning and optimization, including geocoding, network design, even workforce scheduling. Different levels of transport optimization are possible for one transport depot across multiple transport depots, or for integration of all domestic inbound and outbound transport flows. Before we discuss artificial intelligence or AI, we first have to understand what is AI. AI is basically any program that can sense, reason, act, and adapt. Machine learning is a form of AI in which algorithms improve in performance as they are exposed to more data over time. In short, AI that is capable of learning. Deep learning is a subset of machine learning in which multi-layered neural networks learn from vast amounts of data. An AI program's ability to execute cognitive functions such as learning, reasoning, and problem solving, normally only expected of humans, depends on its ability to collect and process data. Digital data can be input directly from online sources or global positioning systems. The use of visual and audio sensors allows for the capture of video and audio data. Thermal sensors measure ambient temperature, while haptical sensors allow the perception of touch. AI can be incorporated into transport optimization in three main areas. Firstly, an AI-enabled fleet management system can help companies collect a wide variety of data, including traffic and road conditions, weather conditions, environmental hazards on routes, and the system then analyzes the data to help fleet owners make better decisions in routing and scheduling that will in turn improve their operational results. The power of AI and big data can also be used to monitor and identify the maintenance needs of the vehicles in a company. Instead of carrying out repairs only when breakdowns happen or conducting planned maintenance regularly, AI collects data, provides diagnostics, and alerts companies when maintenance is required. This avoids breakdowns, increases vehicle availability, and avoids service failure due to vehicle downtime while optimizing maintenance costs. Lastly, robotic process automation or RPA can be used to automate the numerous high-volume, manual, and repetitive processes commonly found in transport planning, such as checking carrier websites for scheduling shipments, preparing shipment documentation, and liaising with clients on shipment details. RPA can be used to automate the end-to-end transport planning process by interfacing with multiple systems, internal and external websites, as well as email. This allows the company to improve staff productivity and achieve high levels of accuracy and consistency. There are many types of optimization software. For example, Autotech was founded by a few young Dutch students in the 80s. Many years later, it is still the world's leading supplier of mathematical optimization software and advanced analytics, with around 1,000 employees and offices in 13 countries around the globe. LlamaSoft, a US supply chain design software business, is considered one of the fastest growing technology companies in North America. Founded in the late 1990s, it offers a number of innovative solutions that help some of the world's best-known brands make smarter, faster decisions about their supply chain. Paragon Software Systems, founded in the US in 1991, is a global leader in developing, implementing, and supporting routing and scheduling solutions. It has a global staff of just 110, but customers in 61 countries. Now let's take a look at a case study about how Coca-Cola, one of the world's top-selling brands, used transport optimization to change the way their business works. In 2005, they distributed 42 billion bottles and cans of their products in North America, total 20% of their worldwide volume. Transport planning had to consider a number of constraints. Due to the vast number of locations, there are varying requirements for specific vehicle types and equipment. Some places required trucks with tailgates, others could only take vans. Correspondingly, the driver had to have the right license type for the required vehicle, and some places also required in-depth knowledge on how to get around the place, such as military bases. Every retail outlet had specific operating hours, which could mean deliveries to supermarkets early in the morning, cafes in the afternoons, and nightclubs late at night. Traffic jams in the city area could lead to vehicles being stuck for hours in the gridlock and would need to be avoided as far as possible. And lastly, Coca-Cola carried varying products with specific constraints, such as temperature requirements and fragile packaging. In 2004 and 2005, CCE implemented Autotech's vehicle routing software. Today, over 300 CCE dispatchers use this software daily to plan the routes of approximately 10,000 trucks. They realized an annual cost saving of $45 million and gained major improvements in customer service. With that, we'll come to the end of Lecture 6. Thank you and see you next time.